Before we talk about different types of oscillators, you should know one important term. It's called Barkhausen Criterion. Barkhausen Criterion. Please try to remember, this may be a new term for you. So we have to know this, or you must know this Barkhausen Criterion before we talk more about oscillators. So we know oscillators are generating particular frequency and it should be sustained oscillation, right? So I told you the beginning of this lecture, the oscillators. So the sinusoidal signal is just going to the positive and then going to the negative side and then positive and then negative and then positive, is repeatedly going up and down, back and forth. So this is creating frequency. So this is 1 hertz, one positive and one negative cycle. This is called 1 hertz. And how many hertz we have here? So we have here 2 and we have 3, and then if I make here, then I have 4 hertz frequency I created by using just for this example. So this frequency signal should be sustained. The amplitude, you see here, amplitude is, for example, if I target plus 1 volt, so I get plus 1 volt all the way. So your oscillator should generate standard or stable frequencies. So it means this 1 volt plus 1 volt should be repeated in all the frequencies. So it's not like I generate 1 volt and then after that it's going down little bit. It's going to 0.8 volt and then 0.8 volt and then it will go down little by little in like this. So I generate 1 volt and then amplitude gets reducing and then going down, going down, going down and then 0. So this is not sustained oscillation. This is not correct. We want some kind of sustained oscillations which can maintain the same amplitude. Okay, so that is called sustained oscillation. So oscillator must produce sustained oscillation, not like this. So this is the simple block diagram of the oscillator. So we are applying some input signal and we have some kind of multiplier circuit or multiplier block, and we are giving this to any amplifier. This amplifier can be, as I said, operational amplifier or transistors. And we are getting the output. And we are taking fraction of the output and feeding back to the input via this feedback network. So feedback network, we can call the gain of this feedback network as a beta. And we know already the gain of the amplifier is A. And we are taking the output and going through this feedback network and then feeding back. And here we are combining this output and this actual input and then sending this as an input to this amplifier. This is just repetitively again and again happening. Okay, so here let us just derive some mathematical expression for this. Now you understand how this block diagram works. So now what is the output mathematically? We can write VO, that is the V output voltage is equal to A times V in, right? So at the output, we have the A and then we have the V in. So A times V in, that is what we are getting at the output. So now what is the output of this feedback network? That is the VF. VF is equal to, we are getting this VO and giving us an input to this feedback network. So whatever the gain multiplied by the input, that is the output. So here, for example, this is the input and this is the gain, and we get the VO is equal to A times V in. Here the same logic. So here we are applying this VO and then the gain is this beta. So VF is equal to beta times VO. This is the output of this feedback network. So this is what I have written here, beta times VO, that is VF. VO already I know this is the expression, this is the equation 1, and this is the equation 2. So I apply this value in this equation. So the equation 1 I apply into the equation 2. So then it will become beta times A times V in, right? So I can simply write this as a beta multiplied by V in. Okay, so now this is the output of this feedback network VF. So remember here we have two gains, we are multiplying them. So this is the gain of the amplifier and this is the gain of the feedback network. So A beta times V in, that is what we are getting here. So this A beta, it's called loop gain. So this is like one closed loop, right? So if you talk about this is a closed loop. So here we are multiplying these two gains, then this is called a loop gain. This loop gain is very, very important in oscillator. Okay, so this loop gain is really important because the produced oscillation is really based on this loop gain. So now we will see little more detail about this. So I mentioned here in this previous slide, loop gain is important. Why loop gain is important? Now we will do some case analysis to analyze this mathematically. Case 1, I assume if A beta is less than 1, what will happen? So here you can see the numerical example. A beta is equal to 0.99 and the V in is equal to 2 volt. So here in the same block diagram, you can see V in is equal to 2 volt and the A and beta multiplication is 0.99, which is less than unity, which is less than 1. So now I apply in the same formula we found in the previous slide. PF is equal to A beta times V in, right? This is the equation number 3. So I apply these values in equation 3, A beta times V in. So A beta is equal to 0.99 and the V in is 2 volt. Then what will I get? 1.98 volt at the output, right? So this VF I am applying here and I am getting here also the same VF. So that is 1.98 volt. This is for one oscillation. So now I am creating this back and forth signal at the output of this block diagram. So I am applying input as a 2 volt. So at the output, I am getting 1.98 volt. And this 1.98 volt applied to this feedback network. And again, it will, based on this gain value, then you will get something here. And then this 1.98 value will be applied here. And then it will be reduced in the next cycle to 1.96 volt if you apply the same formula. And then this will be going a little bit smaller. And then the third cycle, it will become 1.94 or 1.92. Then what will happen? The output voltage will getting lesser and lesser, and finally it will become 0. Then this is not what we want. This is not, because we are applying 2 volt at the input. But if this A beta value is less than 1, then the oscillation will die slowly. So you can observe here, VF got reduced. It means VO also got reduced. It will reduce gradually, or it will be reduced gradually, and it will reach 0. V out will reduce gradually, and finally it will reach 0. So in this case, we get damped oscillations. So this is called a special term or sentence. We use this damped oscillations. Damped means it's just getting reduced. So this is the case 1. So A beta, whenever this A beta value is less than 1, then we get the damped oscillations. So the oscillation will go gradually down and then it will go to 0. So it will be like this. Practically, if you design the oscillator like this, then you will get the oscillation. You will get first oscillation like this, and then it will go little by little down. Finally, it will become 0. So you will get nothing at the output. This is the case 1. Case 2. Now we assume the gain of this entire loop, A beta, is greater than 1. Let us assume some numerical value. For example, A beta is equal to 1.1 volt and V in is equal to 2 volt. So I am applying 1.1 volt and 1.1 volt is the A beta value and the V in is 2 volt. So according to the formula, this is the VF, A beta times V in. So 1.1 multiplied by 2 volt. So this is what we are getting here. That is 2.2 volt, right? 1.1 times 2, 2.2 volt. So this is the VF. VF is 2.2 volt. So we are applying 2 volt, but we are getting 2.2 volt at the output. So what is happening here? We increase the input into certain level. So you can observe here VF got increased. If VF got increased, then this V out will also get increased because this is just happening repetitively again and again. The signal is just very fast. It's flowing through this network. So the signal value will increase more and more. The next round, maybe it will be 2.4 volt. After that, it will be 2.6 or 2.8 volt and so on. So then the output will get increased gradually like this. So you are applying some voltage and this input voltage will get more and more higher, and then it will go to infinitively up. So this is not what we want in the oscillator. So here oscillations are not stable. This is the case 2 when the A beta is greater than 1. In the case 1, when the A beta is less than 1 also oscillations are not stable. Okay, then what we want? Then we go to the case 3 analysis. So here we make this A beta value is equal to 1 unity. So again with some numerical example, A beta is equal to 1. It's not 0.99 volt or it's not 1.1 volt. It's exactly 1 equal to 1 and V in is equal to 2 volt. So now what's happening? So V in is equal to, so now V in is equal to 2 volt and A beta is equal to 1. So if we apply these values in the same formula, in the same equation, so we get 2 volt at the output. This is the constant value, 2 volt. So the output is not reduced, it's not increased, the same as the input. And we are applying this one here. And this is going to just repetitively applying to this amplifier section, and then it will just applying to this feedback section. This 2 volt will just rotate again and again in this loop. So in this case, what we will get? So it means VO, this output stays at constant value 2. So in this case, we will get constant amplitude in the oscillations. This is our target or our goal. So we do not want the oscillation to die like this. And we do not want the oscillation to increase more and more. We want the stable value, right? So this is what we want. So if you want to achieve these stable oscillations, then you have to have this A beta value is equal to 1. This is the condition. So now we get sustained oscillations, because sustained oscillations we call because we get constant amplitude value at the output. Okay, so here oscillations are stable. So it's also called undamped oscillation. So if it goes down, then we call that as a damped oscillations. And this is a very stable one. So we call this is a undamped oscillations. So now we had seen 3 cases. The third case is the best one. This is what we want. So we have to maintain this A beta value is equal to 1 always when you implement oscillator. So what this Barkhausen criterion is telling us, so it's giving us two conditions to get sustained oscillation. So if you really want to produce sustained oscillation at the output of the oscillator, the same amplitude value, it's not exactly the same, but I mean, this is the same amplitude value. So this guy is giving us two conditions. The first condition is A beta value is equal to 1. It means the overall gain of these two stages must be equal to 1 overall gain, that is the gain multiplications. And the condition 2 is the angle this is angle, it's not angel, this is angle. So this angle must be 0 degree or 360 degree. So phase difference between the input and output must be equal to 0 degree or 360 degree. For example, I give input signal like this. At the output, I also want the same phase. First, we want the same amplitude. That one we can achieve by having this loop gain is equal to 1. Now, if I want to have the same phase without any phase difference between input and output, then I must have this this condition. So this angle of this A beta is equal to 0 degree or 360 degree. So 0 degree means what? So output signal is same as the input signal. 360 degree means it's still the same. So for example, sometimes I get 180 degree phase shift in this amplifier stage. For example, if I use the operational amplifier minus plus, I apply the input to this negative input terminal. Remember, in the operational amplifier, whenever I give the input to this negative terminal, at the output, I will get the opposite, right? 180 degree phase shift. So the output, I will get the start from here. This is called phase shift. So now output and the input, this is the input and this is the output. It's not the same. The phase got changed. This is 180 degree got shifted. So in that case, I'm going to send this to this feedback loop or feedback network. Then this feedback network should also give me 180 degree phase shift. In that case, 180 plus 180, it's going to be 360 degree. So it means again this will be corrected. Then I will get output without any phase difference. So this is what I want. So Barkhausen criterion is giving us two conditions, two important conditions to get the stable oscillations at the output. Stable oscillations at the output. It means first one is the overall loop gain must be equal to 1. And the second one is the phase difference between input and output. Phase difference between input and output should be equal to 0 degree or 360 degree, 360 degree. Then everything is okay. So whenever we have some input and we will get the output like this, very standard one. This is not exactly the standard, like this. The stable amplitude and the phase difference 0. There is no phase difference between input and output. Output is same as the input. So this is called Barkhausen criterion. So if you design any type of oscillator, you can use the RC component or LC component, or you can use operational amplifier or transistors, anything. If you design the oscillator must fulfill these two conditions in order to get the stable oscillation at the output. So this Barkhausen criterion is very important. Try to remember.